Welcome to MEI Modelling with Algorithms. We're on the topic of Graphs and Networks 1, Modelling, and we're on to video 1.2, Modelling with Graphs and Networks. Starting with a bit of history, here we have the famous Bridges of Königsberg problem. The question is, can you take a walk around this town that uses each bridge exactly once and then gets you back to the place that you started? This is a question that Leonhard Euler considered and was able to resolve in 1736. To help to think about this, we can sort of move from an actual picture of the town itself to a slightly more idealized version, and then on to something that you'll recognize from the previous video as a graph representing the situation. And this goes to the idea of modeling, where we're using these graphs to model real-life situations. Now, feel free to have a think about this problem yourself. Maybe work on the graph here. Can you find a way of getting around this graph where you start and end at the same node and you use each arc exactly once? If you want to try that, you can. But what you will find is it actually turns out to be impossible, and that's for reasons that Leonhard Euler figured out, which is essentially that if you are crossing through this node, you have to arrive via one arc and leave by another. So that means that the arcs have to be paired up if you're going to achieve this. And because we have some, in fact in this case all of them, but if you have any nodes which have odd order, then it's not going to be possible to do this. Here are three more graphs. You might want to think for these ones whether that is possible as well. For each of those ones, is it possible to start at a node, go around the graph using every arc exactly once, and returning to the node that you started at? Well, for graphs for which that is possible, we call those Eulerian graphs. And what you find is that there are some graphs where that is not possible, but it is possible to do it if you start and end at a different place, and those are called semi-Eulerian graphs. Another word for an Eulerian graph is one which is traversable, and as I mentioned before, you can identify an Eulerian graph because it is one that has no nodes that are of odd order or odd degree. Okay, so every node has to be even. And for semi-Eulerian graphs, then they will have to have exactly two odd nodes, and it is those two odd nodes that will be the start and the end point. So now we're going to see a very different application of the modelling that we can do with graphs. Have a little read of this question and see if you can think back to something that was in the first video that might help us here. Okay, if you've had a moment to think about that, hopefully it's occurring to you that we can model this as a graph if we think about the people and the flavors as being our nodes, and whether someone likes a flavor or not as being a connection. So a very abstract way of doing things, but it makes sense to represent this using a graph. And in particular, it makes sense to use what's called a bipartite graph, because we've got two different types of thing here. We've got the people and we've got the flavors. They can be put into two distinct groups. So the first thing to do then is going to be to label the nodes, like so. And now if we read through the question carefully, we can add a connection every time somebody likes a particular flavour of cake. So Alfie would like ginger or chocolate, so there's a connection from Alfie to ginger, and there's a connection from Alfie to chocolate. Then it says Callum would like lemon or ginger, so Callum has got a connection to ginger and a connection to lemon. Elliot would like lemon or coffee, and then Joe would be happy with anything except lemon, so that means he'd be happy with coffee, or with chocolate, or with ginger. Like that. So now we've represented this situation. Now we need to see if this can help us to answer the question. So is it possible for them to each to get a cake that they would like? Again, you might want to pause the video here and see if you can decide that for yourself. And actually it turns out when we looked at it this way, it seems like it's fairly easy. So for example, we could say Alfie has chocolate, Callum has ginger, that sorts out those two. Then Elliot can have lemon, Joe could have coffee. There may be other ways of doing it as well. So really what that has achieved, aside from anything else, is just a way seeing that it is possible to model all sorts of different situations using graphs. A very common type of situation that will lend itself to modelling with graphs, of course, are actual road networks linking together towns, and that's what we can see here. In this case, the connections are actually representing bus routes. An important thing to remember all the time here, though, is that with graphs, they're not actually physically representing where these towns are. So it could be that that's a rough representation of where the towns are and where maybe roads are that go between them, but actually that doesn't have to be the case. So all we can actually see here are what towns there are and what towns have got bus routes between which. Okay, that's the only things that we can tell by looking at that. One thing that we might like to be able to tell, but we actually can't at the minute, is what route might be the best for getting, say, between Cheddar and Street. There is one direct route. It may turn out that it's quicker or cheaper to go via Wells or via Glastonbury. Who knows? That information is not there. But that brings us quite naturally to the idea of a network. Now, the difference between a network compared to a graph is that a network's got everything a graph has got, except it also has these numbers, these values or weightings associated with each arc. Now, these weights can represent all sorts of different things, and we haven't said yet on this graph what they represent, but obvious things could be the time it takes for that bus journey, or the distance of that journey, or it might in some way relate to the price of that journey. A nice way of representing that information, rather like we saw in the first video with incidence matrix, is to have a matrix and to actually put those numbers into the matrix to make it more concise. So let's do that. This time, of course, we need to think about what to do when there is no connection. It doesn't make sense to use a 0 now, because that could be interpreted as meaning that there's 0 distance between the town, or that it's free to travel, or something like that. So we need some kind of null character, and more often than not we use a dash for that. So where you see dashes in a moment, it's just going to represent there being no connection there. So there we have the matrix completed. Notice that this is undirected, but in theory we could have a directed network here with arrows on the arcs, in which case we might have a different number in that square to that one, for example. Now, just to preview what's going to come later in the course then, once we've got this information represented in the network, we might want to think about what sort of questions could we ask, what sort of problems might we try to tackle. So, an obvious one might be, what is the quickest route between two given towns? Okay, it'd be fairly easy on this one to figure that out, but on a larger network that might take a bit of work. We might need an algorithm in order to do it. Another question we might ask is, say I want to go out on a day trip and visit all of these towns and get back to the town that I live in. What would be the easiest way of doing that? Or it may be, for whatever reason, that I actually want to go out one day and use every single route that there is. Can I do that? Can I do that by without using the same route more than once? What options are available to me in that regard? Or another thing we might want to think about is, suppose you're the bus company, you want to save a bit of money, for example, and actually get rid of some of these journeys how can you do that and make sure that it is still possible to get from each town to every other town? What would be the minimum that we could be left with in order for that to work? So in terms of what we'll be talking about in this course in particular, that thing I just mentioned, minimum spanning tree, shortest distance between two places, shortest paths. And another thing we're going to talk about is flow in the context of situations where these things are representing flow. And finally then, just to put this into a more broad context, why are we doing this? Well, in the real world right now, people are out there using the sort of mathematical techniques and ways of thinking that we're just starting to touch on here, using computers to help them, using algorithms, but fundamentally in a lot of this work which is happening right now in the real world, we're using the idea of graphs and networks in order to model real situations. Okay, and the range of situations which can be tackled with these things is very wide indeed. So that concludes video 1.2, modelling with graphs and networks. The third video in this topic will be 1.3, further modelling with networks.